Alright, so let's take a look at problem number 5. We want to find the domain of this new function f times g. I do not have to find the equation for f times g because I can use the domain of f and the domain of g to find the domain of this product. So let's find the domain of f. Well, our domain, remember, the domain is a set of all real numbers, excluding any values that cause division by 0, and excluding any values that cause us to take the square root or the even root of a negative number. I do not have any radicals, I don't have any square roots, but I do have a variable in my denominator. So this 3x minus 12, we want to prevent it from equaling 0. But we temporarily solve this so that we can figure out what to... We actually let it equal 0 so that we can solve the equation. We know that 4 satisfies this equation, so now we know that we want to exclude the number 4 from our domain. So the domain for the set of f will be all real numbers excluding 4. On a number line, you would shade all of the numbers except 4. So we put a hollow circle around 4 to indicate that. Shading the arrows is indicating that it's going on forever to the left and forever to the right, that we have the domain of f is all real numbers from negative infinity to positive 4, excluding positive 4, all the way up to positive infinity. Alright, so that is not our answer for A. That is just going to help us get the answer for part A. Now, let's come over and look at G and find the domain of G. Well, it's whenever we're finding the domain from an equation, they say it's a broken record. In the days of record, you would have records that skip, but you guys have probably never listened to a record. Here we have a variable in a denominator and a variable underneath a radical. So this 16 minus 2x, it has to be 0 or positive to be underneath a radical, but it can't be 0 because it's in the denominator. So this has to be strictly greater than 0. If we solve this for x, 8 is greater than x is the same thing as saying that x is less than 8. On a number line, we have 8. Less than 8 is to the left. So the domain for G is from negative infinity all the way up to 8, but not including 8. Now, to find the intersection, we have to describe the numbers that are in this set and that are in this set. So a convenient way to do that is to draw a picture of 3 number lines. Let's include 4 and 8, they were the numbers of interest, in each number line. Alright, so in the domain of f, it was all real numbers, excluding 4. In the domain of G, it was all numbers that were less than positive 8. So we start with our boundaries. 4 is not shaded in both. It's not a member of both sets, so it's not a member of the intersection. 8 is not a member of both sets. It's not a member of the intersection. To the right of 8 is not in both sets. It's not in the intersection. In between 4 and 8 is in both sets. So numbers between 4 and 8 are in the intersection because they are in this set and they are in this set. Therefore, they're in the intersection. Numbers that are less than 4 are in both sets, so therefore they're in the intersection. So here's a picture of what our domain of this new function fg is. And I didn't even have to find the equation for fg to determine the domain. The interval from -4 to -infinity to +4, and we need an open parenthesis because we have a break there, union 4 to 8. So there's our final answer for part A. For part B, let's bring along our work that found the domain of F and the domain of G. Oh, sometimes if it's slow to paste, it means the program's going to crash. Alright, now to find the domain of F over G, it's the domain of F intersected with the domain of G, which is what we just did to find the product. This part we already have, but we also have to make sure that G of X is not 0. So we temporarily let it be 0 to solve the equation. If a fraction reduces to 0, it's not because of the denominator, it's because of the numerator. So if x were allowed to equal 0, then g of x would equal 0. That's in a denominator. We don't want that to happen. So we have to throw 0 out of our set. So was 0 in this intersection? Well, yeah. So remember what our picture looked like before. The picture of this intersection was right here in blue. I wonder if it'll let me steal that. It sure will. So that is this part. Well, we need to find 0 on this. 0 is less than 4. And we need to exclude that 0. So we do not want 0 in this set. So the domain of f over g is from -infinity to 0, union 0 to 4, union 4 to 8. Ta-da! That is our answer for B. Let's see if it will allow me to copy this again. It did before. Yes, it did. So here was our work for the domain of f and the domain of g. To find the domain of g over f, it's the intersection of these two sets, which we already found in part A. We already know what that set looks like. We want to intersect it. We do not want this denominator, f of x, to equal 0. So when will f of x equal 0? Well, since f of x is a fraction, we're interested when a fraction reduces to 0, it's because of the numerator. We do not want to allow x to be negative 8 in the domain, because if we tried to substitute x equals negative 8 into this new function g over f, the function f would be 0. You'd be dividing by 0 and you wouldn't have a corresponding y value. So 0, no, negative 8 is what we're excluding. So this time 0 is okay. So we go back to just the intersection of f and g. And we have to exclude negative 8. Well, negative 8 is to the left of 4, positive 4. We want to come in and punch a hole, exclude that from this set. See, this time 0 is okay. The 0 that we excluded last time causes g to be 0. Well, now that g's in the numerator, hey, that's fine. That's not a problem. We can't allow the denominator to be 0. So our domain, I guess it doesn't matter which color I use, the domain of g over f is from negative infinity up to negative 8, excluding negative 8, up to 4, excluding 4, up to 8. Here is our final answer for part C of problem number 5. So I hope that helps.